Hey everyone, we're going to put on our investigative hats and play medical detective as we decode the beautifully complex world of hemoglobin variants and thalassemias. If you've ever looked at a blood panel and wondered, how do we actually pinpoint these tiny molecular variations that have such massive clinical impacts? Well, you were in the exact right place. Let's get started. Okay, let's dive into this with a quote that perfectly sets the stage for our entire investigation. Hemoglobin analysis is not simply run HPLC and read the peaks. You see, doing this right isn't just about glancing at a printout from a machine. It demands a totally holistic integration of multiple clinical data points. We have to look at CBC indices, peripheral morphology, iron status, quantitative fractions, and sometimes even family history. We are solving a giant puzzle, and the machine's output, that's really just our very first clue. To crack this molecular mystery, we've broken things down into 6 quick chapters. First, the normal baseline. Then, tools of the laboratory, spotting structural variants, decoding thalassemias, diagnostic pitfalls, and finally, the integrated diagnosis. Chapter 1. The normal hemoglobin baseline. You know, every good detective needs to know exactly what a normal scene looks like before they can start spotting the anomalies, right? So let's establish that baseline. So, looking at this developmental timeline, you can see hemoglobin isn't static. It actually shifts as we grow. We kick things off with embryonic hemoglobins, but by fetal life, hemoglobin F, or fetal hemoglobin, totally takes over. Why? Because its high oxygen affinity is absolutely perfect for pulling oxygen right from the maternal circulation. But check out point 3. After birth, we see this critical switch from gamma chains to beta chains, making hemoglobin A dominant. This physiologic switch is exactly why a newborn with severe beta-thalassemia might look perfectly healthy at first. Their disease only unmasks itself as that protective fetal hemoglobin drops off during those first few months of life. Once we hit adulthood, a healthy hemoglobin profile looks pretty much exactly like this. You've got your dominant hemoglobin A making up a massive 95 to 98%, but I really want to draw your attention to that tiny little sliver of hemoglobin A₂, hovering right around 2 to 3.5%. The International Council for Standardization in Hematology makes a huge deal about precisely measuring this specific fraction. And why is it absolutely crucial? Because the difference between a totally normal individual and a beta-thalassemia carrier is an incredibly narrow margin of just a single percentage point or two. It is tiny. Section 2. Tools of the laboratory. Now that we know what normal looks like, let's check out the tools of our trade and see how we separate these tightly packed molecules. Our first major tool is high-performance liquid chromatography, specifically cation exchange HPLC. Basically, we inject our hemoglobin sample into a column packed with a charged stationary phase. As we tweak the buffer gradient, different hemoglobin molecules release and drop out, or elute, at characteristic times. We call this their retention time. But, and this is a massive warning for any diagnostician out there, a retention time is just a clue. It is not absolute proof of identity. Totally unrelated variants can, and honestly do, elute in the exact same time window. Because of those limitations, HPLC isn't our only workhorse. We also rely heavily on capillary electrophoresis, which separates molecules based on charge and electrophoretic mobility. When we put these two powerhouses side by side, we see HPLC is phenomenal for rapid, automated quantification of hemoglobin A₂ and F. But capillary electrophoresis, it's often way better at separating certain tricky variants, like pulling hemoglobin E away from hemoglobin A₂. Neither machine is universally superior. So the crucial point is this brings us to the golden rule of the lab, orthogonal separation. Because different hemoglobin variants can act exactly the same under one single analytical condition, you absolutely must use 2 different physical-chemical methods to confirm an ambiguous phenotype. If your HPLC spits out a weird peak, you confirm it with capillary electrophoresis, or acid electrophoresis, or even molecular DNA testing. You never, ever rely on just one single dimension of data. Chapter 3. Spotting structural hemoglobin variants. With our tools calibrated, let's meet our primary suspects. Variants like hemoglobin S, C, D, and E. Let's look at a classic heterozygous presentation, sickle trait, or HbAS. In a typical adult with this trait, you'll see a roughly 60-40 split between hemoglobin A and hemoglobin S. This ratio is incredibly important. The normal beta-A chain actually has a physiological production advantage over the mutated beta-S chain. So that means hemoglobin A should always exceed hemoglobin S in a simple trait. If you're ever looking at a lab result and hemoglobin S is higher than hemoglobin A in what's supposed to be a trait patient, your internal detective alarms should be blaring. You need to reconsider that diagnosis right away. Now, what's really interesting about this slide is how it highlights one of the most dangerous differential diagnoses in hematology, distinguishing true sickle cell anemia, HbSS, from sickle beta-thalassemia. In both of these conditions, hemoglobin A is completely absent and hemoglobin S is dominant. So how on earth do you tell them apart? Well, you have to hunt for other clues. The MCV, or red blood cell size, is typically way lower in the thalassemia variant. Plus, hemoglobin A₂ is often more clearly elevated in sickle beta-0. But you've got to be super careful here because hemoglobin S can actually distort the A₂ measurement on some HPLC machines. Section 4. Decoding thalassemia syndromes. Let's shift our focus a bit from structural variants to the thalassemias. Now, a really fascinating exception that bridges both of these worlds is Hemoglobin Lepore. This is a super unique fusion hemoglobin created by a genetic unequal crossing over between the delta and beta globin genes. What makes Lepore so wild is that it's both structurally abnormal and it produces a thalassemic phenotype because the fusion gene is just poorly expressed. And to make matters worse, on an HPLC machine, Lepore can actually elute in or right next to the hemoglobin A₂ window. That can falsely elevate your apparent A₂ reading and completely fool you if you aren't paying super close attention. Another tough differential is separating delta beta-thalassemia trait from HPFH. That's hereditary persistence of fetal hemoglobin. Both of these are going to show elevated levels of fetal hemoglobin in an adult. But when we check the red blood cell indices, delta beta-thalassemia shows up with low MCV and MCH, a classic thalassemic picture. HPF, on the flip side, typically presents with near-normal red blood cell indices and even higher levels of hemoglobin F. When the phenotype is ambiguous like this, molecular testing becomes our ultimate tiebreaker. Chapter 5. Diagnostic Pitfalls and Modifiers. We are entering the climax of our investigation now. The laboratory is absolutely full of traps. I want you to ponder this question for a second. We've already established that the exact percentage of hemoglobin A₂ is the absolute key to identifying beta-thalassemia carriers. So, what could possibly cause our multi-million-dollar automated systems to get this critical number completely wrong? Well, here are our prime suspects. First up, hemoglobin E can co-elute directly with hemoglobin A₂ on some HPLC platforms, totally masking the true value. Second, degraded fractions of hemoglobin S can sneak into that A₂ window, falsely elevating it. Third, and this is probably the most important one for everyday practice, a simple iron deficiency can modestly lower hemoglobin A₂. This can literally obscure a borderline beta-thalassemia trait entirely. And finally, if a patient just had a recent blood transfusion, those donor red blood cells are going to alter every single peak on your graph for months. To dodge these traps, the pros use this combined microcytosis algorithm. If a patient has small red blood cells, step 1 is absolutely always checking their ferritin to rule out iron deficiency. Got it? Only once iron is normalized do we move to step 2, which is checking hemoglobin A₂. If A₂ is elevated, we confidently suspect a beta-thalassemia trait. But if A₂ is normal or low and we still have unexplained microcytosis, step 3 dictates we have to actively suspect alpha-thalassemia or just go straight to DNA testing. Section 6. The Integrated Clinical Diagnosis. This is it, the final verdict, where we put all the pieces of the puzzle together. And this brilliantly illustrates how we bring it all together. Looking at these two profiles reveals one of the absolute best clinical pearls in hematology. Patient A has microcytosis with high hemoglobin A₂. That is a classic, straightforward beta-thalassemia trait. Easy. But look at patient B. They have microcytosis, normal iron, and a completely normal HPLC output. A novice might just write down no hemoglobinopathy and call it a day, but we now know that a completely normal adult hemoglobin separation right alongside microcytosis is the hallmark, flashing neon sign signature of alpha-thalassemia trait. Now, you might also run into the number 13. This is the Mentzer index threshold. It's calculated simply by dividing the MCV by the red blood cell counts. A ratio under 13 heavily suggests thalassemia, while over 13 leans toward iron deficiency. But wait, there is a major catch here. This is merely a screening heuristic. A mixed iron deficiency with thalassemia can easily defeat this math, so it should absolutely never replace formal iron studies and hemoglobin analysis. I want to leave you with this final, truly provocative thought. Picture this. On an alkaline electrophoresis gel, hemoglobin D Punjab migrates to the exact same visual position as hemoglobin S. If a laboratory technician blindly reports that band as hemoglobin S without using orthogonal testing to confirm it, they might diagnose a patient with a benign trait. They completely miss that this patient's future children could be at risk for a severe sickling disease if their partner is also a carrier. The stakes of precise integrated molecular testing aren't just academic, folks. They literally dictate the reproductive futures and lives of entire families.